All right, 6.4, proportional reasoning, is going to conclude our chapter 6. And in this section, we're going to talk about how ratios are used for comparison and proportions used within them. So ratio notation can be written as A colon B, A over B, and either way we read it as A to B. So that is our definitional notation that we read it as. There's two ways to do ratios. There are part-to-whole ratios and there are part-to-part ratios. So a part-to-whole ratio would be something like this. There's 15 students. 7 of them make an A on the test. So the 7 A's compared to the whole grouping of the students, 15, is a part-to-whole ratio, 7 to 15. But we could also compare the A's to the people who did not make A's. That's a part-to-part ratio. So if there's 15 students and 7 made A's, that means that's 8 of them that didn't, then the part-to-part ratio would be considered 7 to 8. And it's valuable to think about that when you're working through, and we will encounter this again in Chapter 9, this idea of part-to-part and part-to-whole. But you've seen this used before in context of classrooms, so we're going to do a couple of examples with classrooms. We're going to do ratio of boys to girls in a class. So the ratio of boys to girls in a class is 2 to 3. And it wants us to change this and find out what is the ratio of boys to all of the students in the class. So what this is saying, when I have 2 to 3, is that for every 2 boys, there are 3 girls. It doesn't mean there's 2 boys and 3 girls, right? But for every 2 boys, there are 3 girls. And so how many students would that equal in total, the 2 boys and the 3 girls combined? 5. So this is a comparison with 5 students. So for every 5 students, we have 2 boys and we have 3 girls. So when we're trying to create our ratio of boys to girls, we have boys to girls. What I need to figure out how many boys I have to the combined total of boys plus girls. So the number of boys, which was 2, is now compared to the boys plus girls, which is, 5? Yeah. So this is 2 to 5 like this, or you can write it in the colon form like this if you prefer, 2 to 5. So we're just moving from one type of a comparison into the other one. And we can move backwards as well. So if I have 3 compared to 7 of the class are girls, this is saying that I have 3 girls to 7 students. But the students are compiled of girls and boys. And we know how many girls there are. It's 3. So how many boys would that have to mean in that 7? Yeah, it's 4. So if I'm wanting now to compare the girls specifically to the boys, right? My girls are still 3. I'm sorry, the question asked for it, boys to girls, didn't it? My apologies. We'll move this one down. Okay, it wanted a comparison of boys to girls. Okay, so my girls were still 3, so it's now on the denominator. And what are the boys? That was 4. So this is 4 to 3 like this, or you can write 4 to 3 like this. So pay attention to the ordering because I almost missed it. Yep, Cora.
When it comes to putting it in the fraction setup or the colon setup, does it matter which one you do?
It doesn't matter which one you do. When we're using our ratios in a moment inside of proportions, we're definitely going to keep them in fractional form. Some of the things that fractional form sometimes makes you feel uncomfortable about is that if you have a 1 in the denominator, you don't just reduce 3 to 1 to 3. So you can't get rid of a denominator. So if you're going to put it in fraction form, just remind yourself of that. We still will reduce fractions, though. So whether it's written in fraction form or in the colon form, we still need it reduced. So, for example, if our fraction had ended up being, say, 4 to 6, like this, or 4 to 6 like this, either of these notations, no matter which one it is, we would need to reduce them. And so we would end up with 2 to 3 or 2 to 3. So to answer your question specifically, no, it doesn't matter, but there are some sort of benefits to one versus the other, depending on what we're doing with them. All right, so what we're going to do with our ratios is we're going to be able to create proportions. So proportion is a statement that two given ratios are equal. So something like this, A over B equals C over D. And if we have a proportion like this, A over B equals C over D, there are three other equations that hold true. So these are our proportionality theorems. The first one is probably the most familiar. If you cross multiply, right, this is one way to prove fractions are equal. So if A over B is equal to C over D, it would also be true that A times D is equal to B times C. Okay, we've seen that before in a previous chapter, or previous section of our chapter. The next two are a little bit more interesting, though, and you might not have thought of them in this way, but they definitely work. This same ratio is showing up, A over B equals C over D. And what this is saying is that I can take the fractions, and if I flip them both upside down, the ratios would actually still create a proportion, right? So if they're the same when they're right side up, they're going to be equal to each other when you flip them both upside down. That should make sense. The last one, though, is the most unique that you probably wouldn't think would be true. It actually talks about the ability to change a diagonal. So notice it's the same one that we started with here, but if you compare it to the proportion you get at the last part, what you actually see happen is this diagonal is the opposite of what it started as. It's B and C switched places. And there's nothing special about B and C. I could have equivalently switched A and D, and it would have worked too. So by process of like the, I don't know, I'm not sure what word I'm looking for, but it's equivalently true that we could actually say that D over B is equal to C over A and have flipped this diagonal instead. And it would have created equal fractions too. Okay, so you can flip fractions upside down, you can multiply across diagonals, and you can also switch the two pieces along one diagonal or along the other diagonal, and it will work. All right, so what we're going to do next is we're going to actually take a look at some example problems of proportions. So these example problems will have us setting things up in ways that compare them appropriately. So like when we were looking at, boys compared to girls, boys compared to the whole class, we have to figure out what we're comparing in order to make this work. And there will always be two things that we're comparing. One of the things that get compared go from numerator to denominator. The other of the two things that get compared go from the left-hand side of the equation to the right-hand side of the equation. So the first thing we're looking for in the description is what's being compared. So here's what we have for Jim. Jim found out that after working for 9 months, he had 6 days of vacation time. If he accrues vacation time at the same rate, how many days would he earn in 2 years? So can you tell me one thing that's being compared in this? I don't mean numbers or anything, just like concepts. What are the concepts that are being compared here? Okay, the months that he's worked and the days he had as vacation. Does that make sense? So not necessarily months and days, but it's the working compared to the time off, right? So I'm going to write those as a fractional form, one in the numerator, one in the denominator. But I'll show you another setup for that before we move past this problem. So I'm going to do on the top his days off. And it's going to be compared to his months worked. So that's the one that's sort of written in to be compared really clearly. The other one's a little bit less obvious. Can you tell what the other comparison is that's being made?
Years.
Nope. Okay, it's now versus later. What has already happened now? What does he have? How much has he worked? What's going on now compared to what will be happening in the future? Do you see it now? How that's being compared as well? It's not directly written in there, right? It's definitely not, but that is a part of this question. So let's take a look at what happens when we compare these quantities. What about now? How many days of vacation does he have now? 6. And I'm going to go ahead and write the word days in here. You don't necessarily have to, but if you've labeled it on the side, it'll be okay. How about months? How many months has he worked now? 9 months. Okay, so that's currently where he stands. How about the later? What do we know about the later? Yeah, we know that he's worked for 2 years, and 2 years needs to be in 24 months. And Kinsey's exactly right. We need to turn it into months, or it won't make any sense, right? It has to be the same. Yes, Laura?
Is it going to be the 24 months plus the 9 months with it?
No, it's saying that in a total of 2 years is the way it's worded.
Okay.
Yes, that's a good question, though, but it's saying in a total of 2 years, what would he be accrued? Yes. Okay, and then the unknown, the thing we're trying to find is the number of vacation days that he would have at that point, right? So this is the unknown, is the X number of days. So what I usually do is I have all the units on there in my original setup, and then once I start working the problem out, I don't use them. They'll get messy inside of there. But just to make sure that I get them all the pieces in there correctly, because if I don't, I might have accidentally put a 2 instead of a 24 in the place where I put the 24 months, right? If I wasn't thinking about the units when I did that. So I think it's a good idea to be real careful with the units at the beginning, but as we're working the problem out, we don't need them. So we're going to cross multiply to solve the problem. So I have 9 times x, and then I have 6 times 24. So somebody tell me, what is 6 times 24? 144. And then what would I do? Divide by 9. And what is 144 divided by 9? 16. Okay, so it's 16 what? Days. These are his 16 vacation days. Please make sure you write units, because all these word problems are going to have some kind of units involved. Now let me just show you another possible setup, just so that you can recognize how you might also think of this. We originally talked about the comparison being made of his days he's got vacation for and his months he's worked. And I could have done it this way. So this is the days of vacay compared to the months worked. And instead of putting them as the fraction, I could have put them as the two sides of the equation. I could have done that. I still have the now and the later, so I would have now and it would be compared to later, but that could be my fractional comparison instead. And I want to show you what happens when we set this up so that you can see why it works just as well. How many days of vacay does he have now? It's not 6. Was it 6? 6 days. How many will he have later? Well, if we hadn't solved the problem, we don't know, so that would be the X days down here. His months worked was 9 months, and the months he will work is 24 months. Okay, is that all right? Take a look at these two proportions. How are they different? Yeah, there's a diagonal that's been switched, right? That's theorem 622. Okay? So it doesn't matter which of those two ways we set them up. I get an equivalent proportion either way, and I'm able to solve the problem the same way. Okay? So it depends on your perception when you're starting it. So just because you start the problem one way and somebody that you're working with or checking your solution with later started it a different way doesn't necessarily mean either of you's wrong. You might just have one of these other versions of the proportionality theorems that you could take a look at. Okay? All right, let's take a look at example 4. On a city map, a rectangular park has a length of 4 inches. If the actual length and the width of the park are 500 feet and 300 feet respectively, how wide is the park on the map? If you want to draw a picture, you totally can. That's fine. But our goal really is to try and figure out what things are being compared. So what do you notice? What things are being compared here? There's 2 quantities that are being compared. 2 sets of quantities that are being compared.
Inches and feet.
Okay, so when you say inches and feet, what you're really saying is you're saying the real size and like the map size, right? Okay, so that's actually the quantities that we're comparing. So your real size compared to your map size. And those are in inches and feet, like you said. So we'll make sure we put those into our equation when we first start it. What else is being compared? Length and width. So I just chose arbitrarily to start with the fraction and then to do the two sides of the equations, but you could do it differently, just like I showed on the last one. Okay, so what do we know? It says that on the map, the park has a length of 4 inches. So our map is the top and the length is the left, so this is 4 inches. Right? So that's this piece. And then it said the actual width of the park and the length, the length and the width are the 500 and the 300. And they always go in order. So length is the 500 and then the width will be the 300. So the actual length of the park is 500 feet. And the actual width of the park is 300 feet. Does that make sense? And then that means the unknown quantity is my width, which is in inches. So we'll cross multiply. I have 500x equals, and then 4 times 300 would be 1,200. We'll divide by 500. This is actually a context situation where it makes sense for us to give my answer in a decimal, right? So we will do that. It actually is 2.4 inches. We would not talk about this in a fractional sense, so we'll allow decimals for your word problems, even though we haven't talked about them yet. Is that okay? Okay, we're going to push pause there.